Hello! Hi, how's it going? Welcome to this little mini-series. I'm tacking this onto the math section because it's sort of relevant to maths. We're going to be looking at software rendering. That is doing it all by hand. Now, quick question. Why would we want to do everything by hand? Well, there's a number of reasons. Firstly, it's good problem-solving practice. Secondly, I guess it does give us a little bit of insight. So yeah, I mean, if we just use OpenGL or Vulkan or something, have a graphics card, throw the data at it, it handles it just fine. We don't have to worry about anything. But it sort of takes away a little bit from the programming practice. For instance, frustum culling, view frustum culling is pretty useful. It's pretty cool. Wouldn't it be great if I'm working on a GPU-driven rendering system and I have a whole bunch of object descriptions and I can send them to a compute shader and cull them against my view frustum and then use that to record a bunch of draw commands so that I'm reducing my overdraw, even though I don't need to because I'm using Vulkan or OpenGL. And then third reason is it's just fun. It's just plain fun. So in this series, we're going to be going through a number of steps. First of all, we have this session where we just get the project set up. After that, we're going to draw lines and look at line drawing algorithms. Then we're going to do some projection coordinate stuff, get a wireframe cube just projected on the screen. After that, we're going to get that projected cube moving around. We're going to add some transformations to it. Then we're going to clip the cube in view space so that it doesn't get too close to the viewer and it handles it just fine. Then we're going to look at view frustum culling, where we can define a view frustum and cull the cube against that, which will be really useful later on when we want to interpolate attributes such as color or texture coordinates along cube edges. Then we're going to have a look at shading the cube with just a solid color. So rasterizing and filling in the polygons. After that, we're going to have a look at shading with color, one color on each vertex. Then we'll look at texture mapping. And then we are going to create a full 3D scene. Anyway, so I hope that you can be with us for that journey. And yeah, let's have some fun. All right, so let's have a look at the underlying concept for clearing the screen. Every video is going to start like this, more or less. We're going to have a look at the technique. And this technique will apply no matter which environment we're using. I forgot to mention, which environment can we use for these videos? Anything we want. Really just any program that lets us set screen pixels one color at a time. Anyway, I'm providing two, Vulkan or OpenGL. It's up to you which one you go with. But let's start off. So we have something called a color buffer. And a color buffer represents the color of the pixel on each screen. Just for simplicity, I'll go with a 16 pixel color buffer. So it's an array of data. In our case, typically either raw bytes, unsigned characters, or integers, 32-bit integers. But here's how we see things. We see things in memory as if it was a straight line. So we have pixels 0, 1, 2, 3, and so on. And then it's the job of the program, whichever backend we're using, to take that and write to the screen. So what the screen sees is like this. If we have a 4x4 screen, then pixel 0 will be the top left, and we'll go across. But then we've reached the end of the screen, so we read back over. And so if we set this in a loop and just keep setting each of these positions in the array to the same number, then what will happen is the whole screen will get set to the whole color. If I set just the first 4 elements of the array to the same number, then the first line will be set to the same color, and so on. Now, the way the pixels are laid out is typically 32 bits. So we'll have byte 3. And each byte will be a channel. So common format would be red, green, blue, alpha. There will be some variation according to which rendering backend we're using, but it'll be something along these themes. Now, another thing I'm going to look at in this video is not just setting the pixels one at a time, but with C++, we have AVX2, Advanced Vector Extensions, with 256-bit wide registers. And what that means is that we can interpret 8 floating point numbers together as one block, or one vector. So this will be block 0, this will be block 1, and now previously we were using 15 operations to set every pixel on the screen, but what we can do is interpret the color buffer as not an array of 32-bit integers, but an array of these blocks, in which case when I set block 0, I'm setting all of these 8 pixels at once, and when I set block 1, I'm setting all of these 8 pixels at once. So that's what we're going to do in this session. We're going to load up a programming environment, a sandbox. We're going to set the pixels one at a time, and then we're going to write a function, or look at a function if it's already been written, to set the pixels 8 at a time. Okay, so that's enough with the theory. Let's get into the practice. Okay, so here we are getting our programming project environment ready. There are 3 things that I'm going to look at in this video, and these links will be down below. Now, the first of these is a math package which I've created called Linear Algebros. I just wanted somewhere to write my math routines. Now, we could use GLM if we want, but we could also use this. And I'll be using this not in this session, but in later sessions. So let's just go ahead and download zip. Okay, fair enough. Then there are 2 options we can go with. Either Graphics Programming Sandbox, which is just a simple blank OpenGL project for doing this sort of thing, or the Vulkan version. And I'll go through both. So first of all, we'll download the OpenGL version. Download zip. And then we'll download the Vulkan version. Okay, so let's start with the OpenGL version. Here is the zip file that I unzipped, and the project is set up for us, so we can just double click on, I know it's not SDL2 starter, but there we have it. And let me just pop in, let me just run the project first, see what we've got. There we go. So as you can see, we're setting the screen. Okay, fair enough. Now let me just close that down and sort of investigate what's happening here. So yeah, so we have game app and we have a constructor, that's fine. Make window, that is fine. Process input, okay. Run. Okay, so I'm just gonna modify this again, because remember the goal is to clear the screen. So if I just go to the engine class, actually I'll go to the header, and down here I have this right down here, clear screen and clear screen AVX2. Now I'll just cut those and whoops. I'll put them up above so they're public functions. So now that we can call these from our project. So I'll just go back to the game app. And let's go get the renderer, tell it to clear the screen, and let's go, it says we need a vec3. So the color convention here is each channel is going to be between 0 and 1. So if I want to make this screen black, no worries. I'll make a GLM vec3, 0 for the red, 0 for the green, 0 for the blue. Okay, now I just want to head back to the engine renderer function, okay, and I'll just get rid of this, all of this stuff here. So I don't want it to do anything, I just want to clear the screen. Okay, fair enough. Now let's go back to the game app. So I don't want to be too fast here. So again, what we're doing is I'm just setting it so that the render function pretty much just flushes whatever is in the color buffer onto the screen. And the way my app is going is the first thing it does is tells the renderer to clear the screen to black, 0 for red, 0 for green, 0 for blue, and then it flushes that. Okay, so let's run that again. And the screen is, yeah, the screen is black. Just hit escape to end the program. For some reason, this security thing keeps popping up. What? Don't do that. Thanks, Windows. Thanks, Windows. Okay, so let's look at what that clear screen function is actually doing. So we'll go to the engine class. This is what I meant when I said it might be written already for us. So we've got this vec3, so a float for each color component, and we need to turn that into a 32-bit integer. Now, in some past videos, I've talked about ways to do this, but essentially what you do is you get each of the components from a float between 0 and 1 to an integer between 0 and 255. That's 1 full byte. And then apply bit shifts on the various components to get them into the right position, sum those all together, and then the respective bit positions are setting the channels. So let's have a look at flattened color. Crunch color, I mean. Yeah, so that's what I'm doing here. I'm taking the numbers, scaling them up by 255, clamping them between 0 and 255 just to make sure. And then, like I said, byte 3 is the red, so that needs to shift up by 24 bits to get it up to the upper byte. And then we'll shift, yeah, the green and blue. You may have to adjust this on your system if it's not working correctly. But yeah, so there we have it. Now in terms of performance, we can currently see that we are getting about 470, 480, just under 500 frames per second. Now we can modify that by just popping up here, running this in release mode, and then we get up to 2300 frames per second, which is perfectly fine. Okay, good. So all well and good. What about setting 8 pixels at once? Okay, so if we go back to these functions, we have clear screen and clear screen AVX2. Now what we do is essentially the same thing. First of all, we get that color into an unsigned integer, so we can just put it directly on the screen. Then we use the set1 function, and what that does is I've got a course on SIMD stuff if you're more interested, but essentially it sets up a 256-bit register with every float of that set to the same value. So that gives us, 8 32-bit integers in place, ready to go, so we can set 8 colors at once, and then we calculate the number of blocks we need to get. So the number of pixels will be width times height. If we divide that by 8, that will be the number of blocks because we're setting 8 at a time. And then we take a pointer, so we take the color buffer array and reinterpret it as a block pointer. So that sets the stride of the pointer to 256 bits. Typically, if you have an array of floats or something, and you increment the array index, it will step 32 bits forward. However, interpreting this as a block means that we're now stepping 256 bits forward. So it sets it so that we can set the first 8 pixels and then step over to the next set of 8 pixels and keep going like that. So what we can do is then just use that index to set 8 pixels at a time to that color SIMD, which is, it's been set up above. And then just in case we've missed the last few pixels, we just do a little for loop at the end. In most cases, this won't even be necessary because the number will divide evenly by 8. So let's go back to debug. In debug, we were getting just under 500 frames per second. Let's go to the game app. And instead of clearing the screen, we'll just clear the screen in AVX2. Actually, let me just for posterity. And now we've gone from under 500 frames per second to 2800, 2700 frames per second. So that's pretty good. And just why not? Let's run that also in release mode and see how that does. And now it's about the same. Yeah, very interesting. Very cool. Okay. Cool, so that has just been a little spiel on setting up the OpenGL environment. Okay, so we've got that, that's all good. Now let's have a look at doing the same thing in Vulkan. Now guys, remember, I want you to comment, I want your feedback. Which of these backends do you want to work with for the rest of the series? So I've just extracted the Vulkan graphics sandbox that I had before. I'll open up that project. And if we look at, go into control, look at the app. Yes, let me just change that. So back to the same task as before, just clearing the screen. So I'll clear it with all, 0 red, 0 green, 0 blue. Give that a go. So the way this works is we'll have the graphics engine and we'll do any calls to the graphics engine, and then when all the calls are done, we'll just hit render, and same as before, that'll just flush it to the screen. So if I run this right now, again, we're running in debug mode. Previously it was running in OpenGL debug mode, just under 500 frames per second. Let's have a look and see how this one goes. Not very fast. Not very fast at all. That's a little concerning. Anyway, so there we have it. Now, what is this actually doing? Let's go over to the engine. We'll just go over engine. Let's give it a second. Yeah, here we are. Clear screen. So what this engine has is it has a whole bunch of frames so that it can draw to one frame while another frame is up there on the screen. So it selects the frame that it should be drawing to right now, and it calls a conversion function. Now, in the OpenGL version, the conversion function converted to an integer, and it did it with bit shifts and addition. Now, Vulkan, on my system, hates integers. It doesn't like integers for textures or swap chain image formats or anything. So instead of that, I'm going with this unsigned character, essentially just raw binary data. And the system may be presenting to different modes. For instance, I'll run this on my desktop computer and it will run one way, and then I'll put it on my laptop and run it and it'll try to run a different way because the laptop has selected a different Vulkan present mode. So to get around that, I've given the engine a general color conversion function. We can see that here. Now this is a function pointer. So this is the format for a pointer to a function that returns a pointer to an unsigned character, and this star here indicates that this variable is called convert color, and it is a pointer, and it takes 3 floats as arguments. Now if we go over to the engine's choose color conversion function, it queries this based on the swap chain's format. So I have a few pre-built functions which I made. We can pop over to this graphics library and we can see that we're doing something pretty similar. Okay, so we take the input channel, we just clamp it between 0 and close to 1, and then we multiply it by 255, a full byte, cast that to an unsigned integer, put it in place here. So instead of a single 32-bit pixel, 32-bit integer, we've got an array of bytes. So we have, 4 little bytes at once. Now when we go, and we have a different routine down below, it's pretty similar. We just reshuffle the red, green, and blue. Now if we go to the clear screen function, what we do is we go from 0 to width times height, but then we set the 4 bytes at once. So if we take this address, multiply it by 4, and then add a little offset, that will be setting each of the bytes. And there we have it. That's setting the screen. So, but this is the thing. This is the thing. This doesn't work so well if we were to put it into release mode. This is an issue that I haven't quite worked out. So if I run this in release mode, I'm trying to set everything to black. And unfortunately, the color is actually random. So if I were to close this, first of all, performance gets better. That's nice. But if I were to close this and then run it again, it would set to a different color. I'm not 100% sure what's causing this issue, and I do have other systems that work, so I'm not too worried about it. So anyway, if we run it in debug mode, it works fine, but performance isn't so good. If we run it in release mode, the colors are essentially random. So let's have a look at doing the same thing in AVX2. So again, we grab the current frame that we're rendering to, we call the conversion color to get 4 bytes set to the red, green, blue, and alpha that we need. Then so this is a little weird. We take this array of 4 bytes and cast it to a pointer float. So that's saying, okay, the stride now is 32 bits. It's not 8 bits, it's 32 bits. Then we dereference that pointer. So what that does is it simply grabs the memory location, and then it says, well, you are now a float pointer, so you contain 32 bits, and I'm going to grab you. So then it essentially takes those 4 bytes and grabs them all in one go, takes that as a floating point number, and sets 8 of them at once. So it's a little fiddly, but there it is. And don't worry, this is about the most technical this series will get when it comes to the underlying bits and bytes sort of stuff. So then we get the number of pixels on the screen, divide that by 8, that's the number of blocks if we're setting 8 at a time. The same as before, take the color buffer and interpret it as a pointer to a block. So we're setting the stride to 256 bits, and then go through setting 8 pixels at once, and then right at the end do a little loop. Okay, so if we were to run this and set 8 pixels at once instead of 1, how does this do? So as you can see, performance now goes to, well, let's give it a second, about the 3000s in frames per second. And that's running in debug mode. So with Vulkan, we can get a little more performance than we were getting with OpenGL. However, at least right now, it's still being weird. So if I were to run this in release, performance does increase. However, output is random. Okay, so that's it. I mean, in terms of the coding stuff, what I'd like you to do is get in there, download a project. It doesn't matter which project you're doing, because apart from this first session, everything will apply. And yeah, get it set up. So there it is. We've got the screen color changing, and that's a really good first start. So guys, that'll be it for now, but I do really want to know which backing API would you like to use, Vulkan or OpenGL? As you can see, of course, we would want to say Vulkan, however, it does have its issues. So just let me know down below in the comments, and I hope to see you again soon for the next stage where we get lines on the screen. All right, have a good one. Bye.